Hello everyone, this is Rahmat Ali, PGT Physics from Indirapuram Public School, Ghaziabad. In the previous session, we discussed current electricity, conductors, connection of conductors in series, in parallel, EMF of the cell, terminal potential difference, Kirchhoff rules, meter bridge, potentiometer and its application. Today we will discuss the chapter moving charges and magnetism. Magnetic field. Long back, there was an old definition for magnetic field. It was the space around any magnet in which other magnetic substances like iron, nickel, cobalt, etc. show some deflection. But in 1820, Dr. H.C. Oersted performed an experiment. By his experiment, he established a relation between electricity and magnetism. There is a diagram which shows the direction of current and a magnetic needle is kept close to it. When we switch on the current in the circuit, the magnetic needle is deflected. If we reverse the direction of current in the circuit, direction of deflection in the needle also reverses. Ampere swimming rule. This rule helps us in calculating the direction of deflection in the needle. It says that if a swimmer is swimming in such a way that current enters through his feet and moves out through his head, then the north pole of the needle deflects towards his left hand. By this experiment, he proved that magnetic field is produced around a current carrying conductor. In this way, the definition of magnetic field is also to be modified. So, the new definition of magnetic field becomes the space around any magnet or moving charges in which other magnetic substance or moving charge is deflected. Biot-Savart law. This law helps in calculating the magnetic field at any point due to current carrying conductor. There is a diagram. In this diagram, we have a current carrying conductor. We consider a small element, say dl, carrying current I. There is a point P at a distance r making an angle theta as shown in the diagram. Then the magnetic field dB is directly proportional to the current flowing through the conductor. It is directly proportional to the current element, say length dl. It is directly proportional to sine theta and inversely proportional to the distance square. Combining all these parameters, we get dB is directly proportional to I dl sine theta divided by r square. Putting a coefficient of proportionality mu naught upon 4 pi, we get dB equals to mu naught upon 4 pi I dl sine theta upon r square. In the vector form, we can write dB equals to mu naught upon 4 pi I dl cross r divided by r cube. The direction of the magnetic field is obtained using Maxwell's right hand thumb rule. Now, what does this right hand thumb rule say? It says that if we hold a conductor in our right hand in such a way that the thumb gives us the direction of the current flowing through the conductor, then curving of the fingers around the conductor gives us the direction of the magnetic field. Magnetic field at the center of the current carrying loop. Let we have a loop of radius r carrying current I. Consider a small current element on it. Small magnetic field at the center due to it. dB equals to mu naught upon 4 pi I dl sine theta upon r square. This is from Biot-Savart law. As the dl and r are perpendicular to each other, so we can say theta equals to 90 degree. Substituting this value, we get dB equals to mu naught upon 4 pi I dl upon r square. Integrating both the sides in order to calculate the magnetic field at the center of the circular loop due to the whole conductor, we get B equals to mu naught upon 4 pi I 2 pi r divided by r square. Here 2 pi r is the summation of the whole circumference of the conductor. That means we can say B equals to mu naught upon 4 pi I upon R into 2 pi. Here 2 pi represents the total angle described at the center. Direction of magnetic field due to circular loop. Depending upon the direction of current in the loop, magnetic field can be inward or outward. We have a conductor in which current is clockwise, then the upper surface will behave like the south pole of the magnetic field, and if the current in the loop is anticlockwise, then the upper face is behaving like the north pole, and if the current is in the clockwise direction, then the upper face will behave like the south pole. Let us discuss a numerical based on the topic. Let V have a wire bent as shown in the diagram. If the current in the wire is I, then we have to calculate magnetic field at the center. The solution is as follows. Radius of the outermost loop is R1 and the current is clockwise, so the magnetic field due to it at the center B1 equals to mu naught upon 4 pi I upon R1 into alpha. Here alpha is the angle formed by the arc of the conductor at the center. The direction of the magnetic field is inward. Radius of the middle loop is R2 and the conductor is carrying current in the anticlockwise direction. So the magnetic field due to it at the center B2 is equal to mu naught upon 4 pi I upon R2 into alpha. Once again, using the Maxwell's right hand thumb rule, we can find that the direction of the magnetic field is outward. Now we have the third arc of the conductor. The radius of the innermost loop is R3 and the current is clockwise. So the magnetic field due to it at the center B3 will be equals to mu naught upon 4 pi I upon R3 into alpha. The direction of the magnetic field will be inward using the same rule. So the net field at the center B equals to B1 minus B2 plus B3. As B1 and B2 are in opposite directions, so we are subtracting the two fields, and B3 is in the same direction as that is B1, so we are adding it. So that means if the two fields are in the same direction, we will add them, and if a field is in the opposite direction, then we will subtract. So substituting the values of B1, B2 and B3, we get B equals to mu naught upon 4 pi I upon alpha. This factor is common among all the three parameters, so we take it out common and we get B equals to mu naught upon 4 pi I upon alpha bracket 1 upon R1 minus 1 upon R2 plus 1 upon R3. As we have taken the magnetic field B1 to be positive and B2 to be negative, so the net field will be along the direction of the magnetic field B1, which is inward. So the net magnetic field will be inward. Magnetic field at a point on the axis of the loop. This is the second application of Biot-Savart law. Let we have a circular loop of radius r carrying current I. Consider a point P at a distance x from it on the axis of the loop. Let we have a small current element on the loop, due to which we have to calculate magnetic field at this point P. Join this point P with the current element. If this line is making an angle alpha and its length is a, then the small magnetic field at the point dB will be equals to mu naught upon 4 pi I dl sin theta divided by a square. Here a is equals to under the root r square plus x square, and theta is equals to 90 degree because the current element is tangentially to the line joining the point P with the current element. So substituting the values of sin theta, we get dB equals to mu naught upon 4 pi I dl divided by a square. This magnetic field is acting along the direction pk. Resolving dB into its rectangular component, we get dBy equals to dB sin alpha and dBx is equals to dB cos alpha. For whole ring, if we have to calculate magnetic field along x-axis, then we have to sum up the dBx. As dBx is along x-axis, when we move the current element on the whole loop, then the dBx will also move in the loop. As a result, the summation of dBx will be 0, because the opposite part of dBx will cancel each other. Whereas the magnetic field along the component y-axis, say By, will be equals to summation of dBy. So By equals to mu naught upon 4 pi I summation dl into sine alpha divided by a square. As sine alpha equals to r upon a, substituting this value, we get summation of dl is 2 pi r. So substituting this value, we get By equals to mu naught upon 4 pi into I into 2 pi r square divided by a cube. We cancel 2 pi with the 4 pi, so the remainder is 2. We get By equals to mu naught upon 2 into I into r square divided by a cube, as a equals to r square plus x square to the power 1 by 2. So we get By equals to mu naught upon 2 I r square divided by r square plus x square to the power 3 by 2. The direction of the magnetic field is again obtained using the right hand screw rule. Ampere's circuital law. This law helps in calculating magnetic field at any point due to a current carrying conductor. It states that the line integration of magnetic field around a current carrying conductor is mu naught times the current in the conductor. If current in the conductor is I1, I2, I3 and so on, then we can write B dot dl integration for the whole loop will be equals to mu naught times the net current through the conductor. Let we have a long straight conductor carrying current I. Consider a loop of radius r around it. If the magnetic field around the conductor at any point P on this loop is B, then B equals to mu naught upon 4 pi 2I upon r. According to Ampere's circuital law, the line integration of the magnetic field is equals to integration B dot dl, as B is constant on whole of the loop. So integration B dot dl can be written as B integration dl. Again, integration of dl is equal to the circumference of the whole loop. So we can write integration dl is equals to 2 pi into r. So we can write integration B dot dl is equals to B into 2 pi r. From equation number 1 and equation number 2, we get integration B dot dl is equals to mu naught times I. Today we have discussed the magnetic field around any conductor using Biot-Savart law, Ampere's circuital loop, and some applications of Biot-Savart law. In the next session, we will study certain applications of Ampere's circuital law. We will study about solenoid, toroid, etc. That's all for today. Hope you enjoyed the session. Thank you for watching.